In this session, we're going to be exploring what happens with electrochemical equilibria in electrochemical environments. So we're thinking about electrochemistry at equilibrium. Our general method for exploring electrochemistry is to consider what happens at these equilibria. So firstly, we establish this electrochemical equilibrium, and then we disturb this equilibrium by applying an external potential. Now, an electrochemical equilibrium is not the same as a chemical equilibrium, but the definition is we're looking at no net current flowing across the interface. So if we look at what's going on in this interface here, there will be a continuous exchange, a constant exchange of electrons, but there is no net current flowing. So this is a dynamic equilibrium. So this is different from a chemical equilibrium. It is an electrochemical equilibrium. So let's think about the different types of cells that we have that make use of this equilibrium. So the first thing we're looking at is a galvanic cell. So a galvanic cell has a spontaneous reaction which converts chemical potential to electrical energy. When the switch for this galvanic cell is open, no current can flow. So there's an electrochemical equilibrium at the electrode surfaces. We have this continual exchange of electrons at one and a continual exchange of electrons at the other, but there is no net current flowing. However, each electrode is at a different potential. When we close the switch, current is allowed to flow. We get spontaneous oxidation happening at the anode, spontaneous reduction happening at the cathode. And this difference in potential allows the current to flow, lighting the bulb. This particular cell I've drawn is an example of a cell known as a Daniell cell. It is a standard cell for electrochemical equilibria. It's well recognized and well understood. So a galvanic cell relies on a spontaneous chemical process to convert to electrical energy. So what other types of cell do we have? Well, the electrolytic cell is the second type. These ones have a non-spontaneous reaction. And these ones rely on putting electrical energy into the cell. And it drives a non-spontaneous process. The example I've put here is electrolysis of water. So we have a power supply, which applies a potential difference, which forces those Fermi levels to change, which creates a reaction at each surface. It raises the potential of one, lowers the potential of the other, and drives the reaction forward. Rechargeable batteries are an example of something that behaves as both types of cell. So a rechargeable battery is galvanic on discharging, so it's supplying electrical energy to the appliance, using that chemical energy to generate the electrical potential. But when we want to put energy back into it for storage, it becomes electrolytic as we charge it. So it stores that electrical energy as chemical potential. The next phase of equilibria we want to look at is the Nernst equation. So just a quick recap on this. You covered this in year one. I've linked the video below. This relates electrode potentials to free energies, and there are several ways to represent this. But the main way that we're most familiar with is this form of the Nernst equation, where we're looking at how the electrode potential varies according to the number of electrons exchanged and the reaction quotient. So it modifies the standard potential for our real reaction conditions. So remember, the reaction quotient, whenever we're looking at equilibria, is a product of the activities of the right-hand side divided by the product of the activities of the left-hand side. You remember doing this as a product over reactants, but when we're dealing with equilibria, we don't really have products and reactants, so we need to look at the different sides of the equation. We normally use concentrations rather than activities, assuming that the standard activity is unity. This only applies at very low concentrations, however. But it means that we end up with Q being unitless, which makes life a lot easier. So let's think about our reaction quotient here. If we have our general reaction, remember we have the products of the right-hand side divided by the products of the left-hand side, and at low concentrations, activities are approximately equal to concentration, so we can use this approximation. This doesn't tell the whole story, of course. We need to look at the half equations, those reduction half equations, to find the number of electrons that are being transferred. This allows us to establish the value of n and therefore use the Nernst equation. Whenever we're thinking of using these reactions, we need to consider what phases we're working within. So we're wondering whether we're looking at solids, liquids, or gases. So the first thing to do is start with the half cell reactions. So by convention, we always write these as reductions. So if we consider the phenomenon of the electrolysis of water to release oxygen gas, we have liquid and gas present. So we have liquid water, we have gaseous oxygen, and we have aqueous hydrogen. So how do we treat the reaction quotient? How do we consider a concentration when we have bulk liquid and bulk gas? But whenever we're thinking of the solvent, remember we're thinking about activities. The activity can be taken as unity because it is the solvent, and the activity doesn't change significantly as part of the reaction. So because it's not changing, we can accept it cancels out as 1. For the gas, we want to consider the partial pressure, so the partial pressure of oxygen. Since the gases we're almost always working with at atmospheric pressure, and they're being evolved at atmospheric pressure, and they are pure gases at the point of evolution, we can also take these as being unity. So this allows us to simply consider this in terms of the aqueous terms. Now we need to make sure we look at our pressures, look at our concentrations to make sure that that still applies, but almost always our gases and our solvents will be considered under standard conditions. So let's apply the Nernst equation to a full cell. So using this, we can predict the variation of cell potentials, the spontaneous direction of reaction, free energy change. Okay, this is a recap from what you've done before. So let's think about the technique that we're going to use. So the first thing we need to do is we need to write down the cell. So we're going to use the copper hydrogen cell that I've detailed here. The first thing we need to do is we need to write down the cell, remembering to balance our half cells. So if we look at our two half cells, we can see that we don't have an equal number of electrons. So firstly, we need to balance the electron term. We're going to do this by multiplying the second one by 2. So we get 2H plus 2E minus going to H2. And the standard cell potential is unchanged by this operation. It's still going to be the same potential even if we've doubled up. Okay, so that gives us something that we can equate. We now subtract this from the copper equation, and what we end up with is the overall cell reaction, which allows us to identify our left hand and right hand side. So our overall cell equation is copper 2 plus H2 goes to copper solid plus 2H plus, and our standard cell potential is simply the difference between the two, which in this case is 0.34 minus 0.0, which is 0.34 volts. Okay, so that gives us our overall cell reactions, where we have our right hand side and our left hand side. So this means that our reaction quotient is going to be the concentrations of the right hand side. So remember, H plus will be squared because we've got that 2 there, divided by concentration of Cu2 plus and the concentration of H2. Now looking at this, we've got copper solid. So the activity of this is going to be unity. So it's not going to be changed by the reaction. It's going to be essentially constant. So we don't need to consider that because it goes to 1. H2, let's say we're working under standard conditions, so we'd expect 1 atmosphere of pressure, so that would be unity as well. So that can disappear as well. So that tells us everything we want to deal with. Great. Are our cells at standard conditions? Well, let's just say that we consider our concentration of protons to be 1 mole per dm cubed, and we consider the concentration of copper 2 plus to be 0.2 moles per dm cube. So we're no longer operating under standard conditions, so we need to apply our Nernst equation to adjust the potential. So we need to find out what the reaction quotient is. Well, fortunately, the proton concentration is 1, but the copper concentration is changed, so Q becomes 1 squared over 0.2, which is equal to 5. And this allows us to apply our Nernst equation. Our Nernst equation then becomes E is equal to 0.34 volts minus RT, so 8.314 joules per Kelvin per mole, times our temperature, we said is at 25 Celsius, that's 298.15 Kelvin. Divide that by NF, so the number of electrons from here, we've got 2 electrons. 2 electrons times the Faraday constant, which is 9.6480 times 10 to the 4 coulombs per mole, and we multiply that by log 5. Okay, let's do some quick approximating. which is 0.34 volts. Firstly, let's consider the units. So our Kelvin cancel, our per mole cancel, and then we're end up with a coulomb, which, if you remember, a coulomb is an amp second. Okay, so that's going to give us our units that we're dealing with. We're working with SI units throughout, so we don't need to do any conversions. So minus 8.314 times 298, that's about just over 8 times just under 300. So we should end up with something that's around about 2,400. 8 times 300, 2,400. Divide that by 2 times 9.6480 times 10 to the 4, which is going to be about 19 times 10 to the 4. Okay, log 5. Well, 19 times 10 to the 4, that's approximately 1900 times 10 to the 2. So this is not quite 1.4 times that, so it's going to be about 0.34 volts minus 2400 by 1900 is going to be about 1.4 times 10 to the minus 2 times log 5. Remember, this is asking what power of E do we need to get 5. E is about 2.7, so it's going to be about 1 and a bit. It's not going to be squared. Let's say that this is going to be about 1.5. So 1.4 times 1.5 gives us 0.34 volts, 10 to the minus 2 minus 0.0. 1.4 times 1.5 is about 2.1 times 10 to the minus 2, so get 0.021. And remember, we need to think about the units, so a joules per amp per second, which is the definition of a volt. So these units are congruent, so they add up. Subtract this, we end up with about 0.32 volts, which gives the overall cell potential using the Nernst equation, adjusting for non-standard conditions. We can go through and we can just check with a calculator. Of course, just checking with a calculator, we end up with, that goes to 2478. This one goes to 19.276 times 10 to the 4, which means we end up with 0.01284 log 5, which gives us, comes out at minus 0.021. So we get the same value with the calculator. Okay, so this tells us how we fix our equilibrium cell potential to give us the overall cell potential for this particular equation, and gives us the direction of spontaneous change. So it's a positive value, so this remains a positive value, which tells us that the direction of spontaneous change is to go to form this copper solid. Once again, make sure you revisit your first year material that you can follow this derivation. We now need to consider what we mean when we say electrochemical versus chemical equilibria. Electrochemical equilibria, as we said, has no net current and are the conditions for measuring cell potential. That electrochemical equilibrium has to be present, otherwise we're not able to measure a cell potential. When we set up our cell like this, our voltmeter has to have a very high internal resistance so that we don't get any current flowing. So we don't allow current to flow, therefore we've got electrochemical equilibria at both electrodes. That allows us to measure that cell potential. Chemical equilibrium, however, requires a slightly different definition. It requires that the delta G for the entire process is 0. So remember that delta G is minus NFE. That means that the cell potential overall has to be 0. But if we allow current to flow, the cell potential is clearly not 0, so we need to reach a different state. So a galvanic cell at equilibrium, remember a galvanic cell is where we have a spontaneous current flowing. At chemical equilibrium, the cell potential will be 0, which means Q equals K. So the reaction quotient is the equilibrium constant. We can use this equilibrium constant because it's related to the standard cell potential anyway. What this allows us to do is it allows us to predict an equilibrium constant from a measured standard potential. So we can get at the equilibrium constant by using the cell potential, which is not measured at chemical equilibrium. So what does this mean? Well, we can find K. Let's consider an equilibrium such as this one, where we have the solvation of silver bromide. It's a sparingly soluble salt. So being able to measure this solubility product, so essentially the equilibrium product for this dissolution, becomes very tricky because we have a very low solubility. So how do we predict it? Well, once again, we can use electrochemistry. So we can use electrochemical potentials to generate a reaction, and we can work backwards from that to determine our equilibrium constant for this dissolution. So these are the two cells that we're interested in, and we just apply the same rules as we did before. We combine these to make the original equation and identify the standard electrode potential for that reaction. Now the key thing is that the overall reaction is not a redox process. This cell is purely hypothetical. So the cell isn't actually real, but we use it for the purposes of this investigation. To do this, we have our two cells. We have our first cell and our second cell. So all we're going to do is we're going to subtract the second one from the first one. This should generate our overall cell potential. So if we do 1 minus 2, we end up with our hypothetical cell becoming silver bromide minus silver plus going to a bromide ion. Now the electron terms balance, so we can use these equations directly. Remember, we've got the first one subtracting the second one, which gives us a standard cell potential of minus 0.788 volts. We can rearrange this equation to give us our silver bromide into silver plus bromide. Okay, now we just apply this relationship here to find our equilibrium cell potential. So our E standard is RT over NF log K. Let's rearrange this, multiply both sides by NF. So log K is E standard NF divided by RT. And once again, this is just a simple case of plugging things in. We have a single electron in the process. We end up with 1 times our Faraday constant, which is 9.6480 times 10 to the 4 coulombs per mole, multiplied by our cell potential times minus 0.788 volts, divided by RT, which is 8.314 joules per Kelvin per mole, times 298.15 Kelvin. Okay, apply the same approximations as we did before. Remember, 8.314 times 298 is approximately 2400. So let's say something like 0.788 times this will give us 7.5 times 10 to the 4. What are our units going to be? Let's quickly cancel some units. Kelvins cancel Kelvin, mole, mole. Remember, we said that a volt is a joule per amp per second, and a coulomb is an amp second. We end up with our amp seconds cancel, our joules cancel, and we end up with a unitless term, which is what we need for our log K to work. Okay, 75 times 10 to the 4, which is approximately 75,000, divided by 2,400. Cancel the zeros. 750 divided by 24 is going to be, well, there are 30 25s and 75, so it's going to be slightly more than 30. Let's say it's approximately equal to 31. Forgive me, we've lost a minus sign. We need to keep that minus sign in. Minus 31. So our K that we get at the end is going to be equal to e to the power negative 31, which is going to be an exceptionally small number indeed. We can apply a calculator again as we did before, and what we find is we end up with, if you multiply the top row out, we end up with minus 7.63 times 10 to the 4 divided by 2478, which when we work that through, we end up with minus, give me the minus, yes, minus 30.78. So we get approximately the same number. What I'm trying to show here is through approximation we can get fairly close to the actual value we're expecting. But what happens if we apply the Nernst equation to half cells? So once again, let's revisit the copper hydrogen cell. We spoke a little bit about what's the sound of one hand clapping. Remember, we can't measure these things in isolation. So every half cell is measured relative to that standard hydrogen electrode. But what does the standard electrode potential actually mean for a half cell? What meaning do we ascribe it? Well, fundamentally, it's a balance point. It's not saying that it is 0.34 volts to drive copper in this direction. It's saying that the copper half cell is 0.34 volts more positive than the standard hydrogen electrode. It's just a relative measurement. So it shows the potential that we would need to apply to switch from galvanic to electrolytic cell behavior. If we want to look at how other half cells compare, we need to think about free energies. We can pretty much measure anything we wish, but it's important that we consider free energies. It's not always possible to directly compare electrode potentials. Remember that not all half cells can be directly measured, so we use this relative comparison between half cells to determine the standard electrode potential for hypothetical half cells, because not all of them can be directly measured. So let's think about the direct reduction of iron 3 to iron. Most electron processes are single electron or pair of electrons. If we think about iron 3 plus, well, we can either add one electron to become iron 2 plus, or for iron 2 plus we can add two electrons to become iron metal. Now we can't combine these because the electrons don't cancel. We can't equate these, we can't multiply them up, nothing's going to cancel out because the electron terms don't work. We can't double this first one because then we'd end up with 2 Fe3 plus and 2 Fe2 plus. We would just end up with 3 iron species in our final equation. So, because the electrons don't cancel, we have to use free energies. We convert these electrode potentials into free energies for each process. So what we do is we simply add both of them together to obtain the overall equation, and then we add the free energies together. So you can see if we add these together, the iron 2 terms cancel out, we gain an electron, and that gives us the overall cell equation here. Okay, but what do we do in terms of the free energies? Well, we just simply work out the free energy for each of them. So the free energy for the first equation simply becomes 1 electron times the Faraday constant times 0.771. The second one becomes 2 times minus 0.44 times the Faraday constant, which gives our final value of plus 0.109 times the Faraday constant, which gives the final cell potential. When we work backwards, we simply apply this equation in reverse, and we end up with a cell potential of negative 0.036. So this allows us to determine the cell potential of any electrode, provided we can establish how we can put it together from the existing measurable electrodes. This is similar to the process I spoke about before with the law of independent migration and the similar principle that you've applied with Hess's law and any other situation where you use a number of known quantities to find the unknown, to close the loop. So we have all of these electrode potentials that we can determine. Remember we said that a standard electrode potential is simply a relative measurement. It's saying that something is however much more positive or negative than the hydrogen electrode. But this means that it can be helpful to have a visual aid. Whenever we think of visual aids, we think of drawing a graph. The way that we typically visualize electrode potentials is to plot current against potential and think about where we're starting, where we're going from. So when we're thinking about electrochemical equilibrium, if we've got a current potential graph, I is 0, so everything becomes single dimensional in this particular visualization. So we're going to plot our standard electrode potentials at I equals 0. Our standard hydrogen electrode, by definition, is at 0. So this is assuming standard conditions where the activity of hydrogen is 1, the partial pressure of hydrogen is 1. Let's look at the copper electrode that we spoke about. So once again, let's say we've got an activity of 1. This is standard conditions, remember, and we have our standard potential marked at 0.34 volts. Our silver electrode, again, standard conditions, has a more positive potential. So what we're saying is that both of these are positive relative to the standard hydrogen electrode, but we're saying now that our silver chloride is 0.46 volts more positive than our copper. Likewise, our copper is 0.46 volts more negative than our silver electrode. These are simply just relative measures, and this graph helps us visualize them. If we change our concentration from standard conditions, we'll get a different potential. So if we take the silver chloride and we reduce the concentration, we find we reduce it to 1 millimolar. We find that applying the Nernst equation, we end up with a drop in our cell potential to 0.62 volts. This is still more positive than our copper electrode. So our overall cell potential we would find by simply finding the difference between the two. In terms of trying to predict what's going on here, If we draw a graph like this, one way to remember it is that whatever is on the right is the species being reduced. So in this cell, we would expect the silver cation to be reduced, while the species on the left, we would expect copper metal to be oxidized to copper 2+. And this gives us a simple way of picturing what's going on. If we then allow a current to flow, we can then apply an external voltage to drive a reaction in a particular direction that we wish. So if we apply a higher voltage, remember this raises and lowers the electrode potentials and drives the reaction a different way. To summarize electrode potentials, it's always helpful to have a visual aid. Our standard cell potential for any system will never change. It's measured under standard conditions. And fundamentally, free energy still govern all processes. Only the free energy can be used to predict the direction of spontaneity. So whenever we have our cell, we would need to formally convert to a free energy to determine the direction of spontaneous change. And concentration has a big effect on cell potentials. So everything's under standard conditions, but the minute we change that concentration, we get a different cell potential. These visual representations can be really helpful to work out what's going on, because sometimes a quick sketch can allow us to just discombobulate the mathematics going on.